Imagine being ridiculed by your superiors, rejected by industry, and called crazy for an idea that would change the world forever. In 1928, a 21-year-old Royal Air Force cadet named Frank Whittle proposed something that sounded like science fiction, a propellerless engine that could make planes fly faster than anything in the sky. Everyone said it was impossible. He was decades ahead of his time. This is the story of how one man's obsession created the jet engine and completely transformed modern aviation. Stay until the end, because the biggest twist in this story comes in the final chapters. Frank Whittle was born on June 1st, 1907, in Coventry, England, the son of a mechanic. Since childhood, he was fascinated by machines and engines. His father, Moses Whittle, owned a small machine shop where young Frank spent hours observing, learning, and tinkering with equipment. That environment shaped his mind to solve complex mechanical problems. World War I was raging when Frank was just 7 years old. He watched with fascination as the planes occasionally flew over his town. These flying machines captured his imagination in a way that would never leave him. To him, airplanes represented the future, freedom, and the limitless possibilities of engineering. At school, Frank wasn't an exceptional student in all subjects, but he excelled in math and science. His teachers noted his uncanny ability to visualize mechanical problems in 3 dimensions and find creative solutions. By the age of 15, he had already decided he wanted to fly and work with airplanes. In 1923, at 16, Frank attempted to join the Royal Air Force as an aviation apprentice. He was rejected twice for not meeting the minimum physical requirements. He was too short, and his build was considered too weak. Most people would have given up. Frank didn't. He spent 6 months doing intensive physical exercises, forcing his body to grow and strengthen. On his 3rd attempt, in January 1923, he was finally accepted. He entered RAF Cranwell, one of England's most prestigious aviation schools, as an apprentice mechanic. There, he would not only learn to repair aircraft, but also have the opportunity to study flight theory, aerodynamics, and aeronautical engineering. During his training at Cranwell, Frank immediately stood out. His instructors were impressed by his ability to understand not only how airplanes worked, but also why they worked that way. He constantly questioned existing designs, always looking for ways to improve efficiency and performance. In 1926, Frank was selected to become an officer cadet, a rare honor for someone from his humble background. This meant he would receive pilot training and formal education in aeronautical engineering. It was exactly the opportunity he had dreamed of. During his training flights, he wasn't just learning to fly. He was studying every aspect of the aircraft's performance. It was during these years of training that Frank became deeply troubled by the limitations of conventional piston engines. Aircraft of the time relied on engines that turned propellers. As aircraft flew faster, the propellers encountered fundamental physical limits. The propeller tips approached the speed of sound, creating turbulence and drastically losing efficiency. Frank began to wonder, what if there were a completely different way to generate thrust? What if it were possible to eliminate the propeller altogether? These questions kept him awake at night, filling notebooks with calculations and drawings. His colleagues thought he was wasting time on impossible fantasies, but Frank had a growing conviction that he had discovered something important. In 1928, at the age of 21, while still a cadet, Frank Whittle wrote a thesis that would change everything. The title was modest, Future Developments in Aircraft Design, but the content was revolutionary. In that document, he proposed for the first time the concept of a jet turbine engine. Whittle's 1928 thesis proposal was elegantly simple in concept, but radically different from anything else before. Instead of using a piston engine to turn a propeller, he proposed using a turbine driven by jets of hot gas to generate direct thrust. The air would be compressed, mixed with fuel, burned, and expelled at high speed from the rear of the engine. The basic principle was Newton's third law. For every action, there is an equal and opposite reaction. If you expelled gas at high speed backward, the engine would push forward. Rockets had used this principle for centuries, but no one had managed to apply it practically to airplanes. Whittle's genius lay in how he proposed to make this work continuously and controllably. Its design included three main components. First, a compressor at the front that would suck in air and compress it. Second, a combustion chamber where the compressed air was mixed with fuel and burned. Third, a turbine that was turned by the hot exhaust gases, which in turn powered the compressor. The gases were then expelled at high speed, generating thrust. What made the idea even more revolutionary was its efficiency at high altitudes. Piston engines lost power dramatically at high altitudes due to the lower air density. Whittle's jet engine, on the other hand, would perform better at higher altitudes where the air was thinner and aerodynamic drag was lower. Airplanes could fly higher and faster than ever imagined. Whittle presented his thesis to his superiors at Cranwell in October 1928. The reaction was mixed. Some instructors found the idea intriguing from a theoretical standpoint. Others were openly skeptical. The problem wasn't necessarily that the physics were wrong, but that practical engineering seemed impossible with the technology of the time. The materials available in 1928 were a serious concern. Temperatures inside a jet combustion chamber would be extremely high, possibly exceeding 1,000 degrees Celsius. Conventional metals would melt or lose structural strength. The turbines would need to rotate at incredibly high speeds, creating enormous mechanical stresses. The necessary precision manufacturing simply didn't exist. Furthermore, no one knew how to design a sufficiently efficient compressor. Axial or centrifugal compressors existed in industrial applications, but not at the speeds and efficiencies required for a viable aviation engine. Each component of Whittle's proposed system presented engineering challenges that seemed insurmountable. The RAF forwarded Whittle's thesis to the Air Ministry for evaluation. In January 1929, the official response arrived. The ministry acknowledged that the idea was theoretically interesting, but concluded that the practical challenges were too great. They saw no viability for development in the near future. In other words, the idea was officially rejected. To make matters worse, the ministry saw no immediate military potential in the proposal. Europe was in a period of relative peace after World War I. Investment in experimental and unproven technology was not a priority. Military budgets were being reduced, not expanded. Projects that did not offer tangible short-term benefits were discarded. Whittle was deeply disappointed but not surprised. He knew his idea was far ahead of its time. However, he also had an unshakable conviction that he was right. The jet engine was the future of aviation, even if no one else could see it yet. The question wasn't if it would happen, but when and who would make it happen. After official rejection in 1929, Whittle continued his career in the RAF as a pilot and instructor. He graduated from Cranwell in 1928 and was commissioned as a pilot officer. Over the next few years, he served in various positions, always distinguishing himself as an exceptional pilot and innovative thinker. But the idea of the jet engine never left him. In 1930, Whittle attempted to patent his invention. He knew that intellectual protection was crucial, even if no one else wanted to develop it at the time. With the help of colleagues, he prepared a detailed patent application describing the principles and components of the jet engine. British patent number 347206 was granted on January 16, 1930. Obtaining the patent was a victory, but also a burden. British patents required annual maintenance fees. For a young officer on a modest salary, these fees represented a significant financial sacrifice. Whittle paid for it out of his own pocket for several years, hoping that he would eventually find support to develop his invention. During this period, he attempted to interest several British aviation companies in his idea. Armstrong Siddeley, a leading engine manufacturer, initially expressed interest in 1929, but later declined. They too felt the technical challenges were too great. Other companies, such as Bristol and Rolls-Royce, did not even respond to his proposals. The industry was comfortable with piston engines and saw no reason to risk unproven technology. Whittle also faced skepticism within the RAF itself. Many senior officers saw him as an impractical idealist, more interested in science fiction fantasies than operational realities. Some colleagues supported him, but most thought he was wasting time and energy on a hopeless project. The phrase "Mad Whittle" began to circulate in some circles. In 1932, Whittle received a momentous opportunity. He was selected to study mechanical engineering at the University of Cambridge. It was a rare honor and a chance to formally develop his technical skills. He enrolled at Peterhouse College in October 1932 and immersed himself in his studies with characteristic intensity. At Cambridge, Whittle had access to top-notch professors and excellent research facilities. He used every opportunity to refine his jet engine calculations and solve theoretical problems. His undergraduate thesis, completed in 1935, included detailed thermodynamic analyses that mathematically proved that the jet engine was not only possible, but would be superior to piston engines in several important metrics. However, even at Cambridge, he faced doubts. Some professors questioned whether the necessary materials could ever be developed. Others pointed out that existing experimental turbines had terrible efficiencies. Whittle argued that with dedicated development, these problems could be solved. But arguments didn't build engines. The financial situation was becoming unsustainable. In 1935, Whittle was unable to pay the annual renewal fee for his patent. With deep regret, he let the patent expire. This meant that his idea was now in the public domain. Anyone or any country could use his concept without compensation. Years later, this forced decision would have significant consequences. Despite all the frustrations, Whittle refused to give up. He was convinced that the jet engine was not only possible, but inevitable. Someone somewhere would eventually build one. He was determined to be that person, no matter how many years it took or how many obstacles he faced. His persistence was extraordinary. In 1935, after completing his studies at Cambridge, Whittle's fortunes finally began to change. He was introduced to two former RAF colleagues, Rolf Dudley Williams and James Tinling, who were fascinated by his idea. Unlike most, they didn't think Whittle was crazy. They thought he was a genius. Dudley Williams and Tinling weren't engineers, but they were entrepreneurs with important connections. They believed the jet engine had enormous commercial potential, even if development was challenging. What Whittle needed wasn't more theoretical studies, but funding to build a real prototype. They were willing to help secure that funding. Through their connections, they were introduced to a financier named Lancelot Law White, who was interested in innovative technologies. White was impressed by Whittle's passion and technical knowledge. After several meetings in January 1936, White agreed to provide initial financial support. It wasn't much money, but it was a start. On January 27, 1936, a company was formally established, Power Jets Limited. The purpose was to develop and eventually commercialize Whittle's jet engine. Whittle held a stake in the company and would serve as chief engineer. Finally, 8 years after his original thesis, he had the resources to attempt to build his own engine. The first challenge was finding an engineering firm capable of manufacturing the components. The British Thomson Houston Company, BTH, in Rugby, agreed to produce the parts under contract. BTH had experience with steam turbines and industrial compressors, so it had at least some relevant expertise. Detailed design work began in March 1936. Designing each component was incredibly complex. The compressor needed to be able to compress air at rates never before achieved in such a compact device. Whittle opted for a dual-flow centrifugal compressor design. Air entered axially and was expelled radially. It was less efficient than an axial compressor, but much simpler to manufacture with the available technology. The combustion chamber presented enormous challenges. Achieving stable and complete combustion at high airflow velocities was extraordinarily difficult. Whittle developed a design with multiple chambers arranged in a ring around a central axis. Each chamber had its own fuel injector and ignition system. The concept was sound, but making it work in practice would be another story. The turbine was perhaps the greatest challenge of all. It needed to extract enough energy from the exhaust gases to power the compressor, while still leaving enough energy to generate thrust. The temperatures would be extreme, and the rotational speeds would be extremely high. Whittle designed a single-stage turbine with specially strengthened blades made from the finest alloys available. Work progressed slowly throughout 1936 and early 1937. Money was constantly tight. Power jets operated on a shoestring budget, and every technical problem consumed precious resources. Whittle often worked nights and weekends, making calculations and refining designs. His health began to suffer due to stress and overwork. In April 1937, the main components were finally ready. The engine was assembled at BTH's Rugby facility. It was a strange and complex device, unlike any engine ever built. Pipes, valves, measuring instruments, and a seemingly endless jumble of metal parts. Whittle looked at his creation with a mixture of pride and apprehension. 9 years after his original thesis, he was about to find out if his idea would actually work. The engine's first test was scheduled for April 12, 1937. Whittle's small team was nervous, but hopeful. They had worked tirelessly for over a year. Now the moment of truth had arrived. The engine sat on a test bench at BTH, connected to numerous instruments to measure temperature, pressure, rotational speed, and thrust. Whittle personally checked every connection and system before authorizing the start. Fuel was added to the tanks. The electrical systems were energized. An external starter motor would be used to initially spin the compressor until combustion became self-sustaining. The crew took up positions behind protective barriers. No one knew exactly what would happen. At 7:45 p.m., Whittle gave the order to start. The starter motor began to turn the shaft. Gradually, the rotational speed increased. At 2,000 RPM, the igniters ignited, and fuel was injected into the combustion chambers. For an agonizing moment, nothing happened. Then, with a surprisingly loud roar, the chambers ignited. The engine roared to life. The hot gases spun the turbine, which fed the compressor, which supplied more air for combustion. The cycle was working. The rotational speed increased rapidly, 3,000 RPM, 4,000, 5,000. The noise was deafening, a high-pitched whistle mixed with a deep roar no one had ever heard before. It was the sound of the future, but then something went wrong. The speed continued to increase uncontrollably. 6,000 RPM, 7,000, 8,000. Whittle yelled to reduce fuel, but the engine wasn't responding to the controls. It was accelerating on its own, fueled by the intensity of the combustion itself. Vibrations increased dramatically. Instruments shook violently. The test rig's frame began to shake. At 13,000 RPM, far beyond the safe design speed, Whittle made the only possible decision: emergency shutdown. He cut off the fuel supply completely. The engine continued to idle, gradually slowing as the crew watched tensely. Finally, after what seemed like minutes but was only seconds, the engine stopped. Absolute silence fell over the test room. Then someone began to laugh nervously. Others joined in. The tension was broken by a mixture of relief and euphoria. Yes, the engine had gone out of control. Yes, it had nearly destroyed itself. But it had worked. For the first time in history, a practical jet engine had operated successfully. Post-test inspection revealed several issues. The fuel control system clearly needed a complete redesign. Some turbine blades showed signs of excessive thermal stress. The bearings had suffered from the extreme speeds. But fundamentally, the concept was proven. Compression, combustion, and exhaust worked together to generate power and thrust. Whittle was elated, but exhausted. That test had drained his physical and emotional energy. In the following days, he suffered a partial nervous breakdown due to years of accumulated stress. Doctors ordered him to rest for a few weeks, but his mind wouldn't rest. He was already thinking about the necessary modifications for the next test. News of the test spread quickly through British aviation circles. For the first time, some important figures began to take Whittle seriously. The RAF showed renewed interest. The Air Ministry requested detailed reports. Maybe, just maybe, that crazy young engineer wasn't so crazy after all. After the April 1937 test, Whittle and his small team embarked on months of intensive redesign and refinement. The engine had proven its concept, but it was far from practical for aircraft use. Every system needed to be improved, every component optimized. The work was meticulous and often frustrating. The fuel control system received priority attention. The runaway acceleration of the first test was caused by uncontrolled positive feedback. Higher RPM generated more compression, which allowed more combustion, which generated even more RPM. Whittle designed a sophisticated mechanical governor that would automatically adjust fuel flow based on RPM and temperature. The combustion chambers were also completely redesigned. The goal was to achieve more uniform and complete combustion. Whittle experimented with different injector configurations, airflow patterns, and chamber geometries. Each configuration was tested, measured, and refined. The process was exhaustive but essential. Materials were a constant concern. Temperatures inside the engine exceeded the capabilities of many available alloys. Whittle worked with metallurgists to identify and test new materials. Special nickel alloys and stainless steel were experimented with. Each new material needed to be tested not only for thermal resistance, but also for fatigue and corrosion resistance. Financing remained a chronic problem. Power jets operated with extremely limited resources. Whittle often paid expenses out of his own pocket. The company was constantly on the brink of bankruptcy, surviving through sporadic capital injections from investors who believed in its long-term potential, even if the immediate results were disappointing. By July 1937, the redesigned engine was ready for further testing. The results were significantly improved. The engine achieved stable and controlled operating speeds. Combustion was smoother and more efficient. The control system worked properly. There were still problems: excessive vibrations, uneven heating, suboptimal efficiency, but the progress was undeniable. Throughout 1938, testing continued regularly. Each test revealed new problems and opportunities for improvement. Whittle developed a deep and intuitive understanding of how the engine behaves under different conditions. He could often diagnose problems simply by the sound of the engine or the appearance of the exhaust. The RAF began to pay closer attention. Officials visited the test facilities and were impressed by what they saw. In November 1938, the Air Ministry finally offered a modest contract for further development. It was an important validation, but the amount was still insufficient to significantly accelerate the work. What Whittle and others in England didn't know was that they weren't alone. In Germany, an engineer named Hans von Ohain was working independently on a very similar jet engine. Von Ohain had begun his work in 1935, a few years after Whittle, but had access to much greater resources through the Heinkel Company. An undeclared race was on. In August 1939, the world situation changed dramatically. Germany invaded Poland, starting World War II. Suddenly, advanced military technology wasn't just interesting, it was urgent. The British government began to wake up to the potential of the jet engine. Additional funds were made available. The project's priority increased significantly. Whittle was promoted to squadron leader and given permission to devote himself full-time to engine development. More engineers were assigned to his team. Better facilities were made available. For the first time, he had adequate resources. But now there was also immense pressure. The war depended on technological innovation. With war in full swing in 1940, the development of Whittle's jet engine took on utmost urgency. The Battle of Britain was raging in the skies. British Spitfire and Hurricane fighters engaged German bombers in desperate dogfights. Speed and altitude were critical advantages. A jet engine could change the balance. What Whittle and the British didn't yet fully understand was that the Germans had already flown the world's first jet aircraft. On August 27, 1939, just days before the invasion of Poland, the Heinkelhey 178 piloted by Erich Warsitz had taken off using Hans von Ohain's engine. It was a historic flight, but one kept secret. Von Ohain's engine, called the HES-3B, had followed similar principles to Whittle's. The similarity was not entirely coincidental. Both were based on fundamental principles of thermodynamics, but von Ohain had developed his ideas independently. He was unaware of Whittle's work until years later. The expiration of Whittle's patent in 1935 meant the idea was in the public domain. By April 1940, Whittle's engine, now designated the W1, was ready for installation in a real aircraft. The Gloster Aircraft Company was contracted to build an experimental aircraft specifically designed around the jet engine. The plane would be called the Gloster E-2839. It was a small, simple design, focused on proving that jet flight was feasible. Construction of the E-2839 was accelerated to the maximum. Gloster engineers worked double shifts. The W1 engine was continually tested and refined during this period. By December 1940, the engine had accumulated over 100 hours of test bench operation, demonstrating increasing reliability. The date of the first flight was approaching. The W1 engine had a thrust of approximately 860 lb-ft, enough to propel the small E-2839 to respectable speeds. It wasn't powerful enough for operational military applications yet, but it would definitively prove the concept. More powerful versions were already being designed, including the W2 with 1,600 lb-ft thrust. By March 1941, the E-2839 was complete and the engine installed. The aircraft was transported to Cranwell Airfield, ironically the same place where Whittle had studied and developed his original idea 13 years earlier. Ground tests began immediately. The engine performed perfectly, but now it needed to prove itself in flight. Taxi tests began in April. Test pilot, squadron leader Peg Sayer, gradually increased speeds as he rolled down the runway. The aircraft responded well to the controls. The engine delivered smooth, consistent power. Small hops were made, lifting the wheels a few meters. Everything seemed ready for the first full flight. The date was set, May 15th, 1941. The weather was cooperating. Clear skies, calm winds. Whittle was present, of course, along with senior RAF officers and representatives from the Air Ministry. The tension was palpable. 13 years of work, frustration, and persistence were reaching a decisive moment. At 7:40 p.m., Sayer received clearance for takeoff. He advanced the throttle gently. The E-2839 began to roll, gaining speed rapidly. The jet's distinctive whistle grew in intensity. At 75 miles per hour, 120 kilometers per hour, Sayer pulled back on the stick. The nose lifted. The wheels left the ground. Britain's first jet aircraft was in the air. The E-2839 climbed smoothly into the afternoon sky. Sayer initially maintained a low altitude, just a few feet above the runway, gaining confidence in the controls. The plane responded well, perhaps even better than expected. The absence of vibration from the piston engine was remarkable. The flight was surprisingly smooth. On the ground, Whittle watched through binoculars, his heart racing. He could hardly believe it was actually happening. His idea, ridiculed for so many years, was literally flying before his eyes. Tears of emotion filled his eyes. 13 years of struggle were worth it in this single moment. Sayre completed a full circuit around the airfield, gradually gaining altitude to approximately 1,000 feet. He tested the controls in different configurations, making gentle left and right turns. The plane handled beautifully. The throttle response was instantaneous, unlike piston engines, which had noticeable lag. After 17 minutes in the air, Sayre lined up for landing. He smoothly reduced power and descended in a controlled approach. The wheels touched the grass with a slight bump. The E-2839 rolled to a stop. Sayre cut the engine and opened the canopy with a huge smile. He had just made aviation history. The ground crew erupted in celebration. Men who had worked for years at that moment embraced each other. Whittle was surrounded by congratulations, but he was in a state of near emotional shock. The relief and joy were overwhelming. He had been proven right. The jet engine worked not just in theory or on a test bench, but in actual flight. Sayre's report was enthusiastic. He described the flight as absolutely satisfactory and noted that the engine delivered smooth, reliable power. The lack of vibration made the flight remarkably comfortable. Throttle response was excellent. The plane reached speeds approaching 600 kilometers per hour on subsequent flights. Impressive for an early prototype. In the following days and weeks, the E-2839 performed numerous additional test flights. Each flight provided valuable data on performance, handling, and reliability. The engine accumulated dozens of flight hours. Minor issues were identified and corrected, but the fundamental design proved sound. News of the success quickly spread to the highest levels of the British government and military. Winston Churchill was personally informed and showed great interest. The strategic importance was obvious. If the United Kingdom could develop operational jet fighters before Germany, it would gain a significant advantage in the air war. In July 1941, the Air Ministry issued a formal specification for an operational jet fighter. Gloster aircraft was contracted to develop what would be called the Gloster Meteor. Whittle and Power Jets would receive contracts to develop production engines. Finally, after years of obscurity, the project had top national priority and adequate resources. However, developing an operational fighter would be far more complex than building an experimental prototype. The Meteor would require 2 engines for reliability and adequate power. The engines would need to be significantly more powerful than the WWII. Weapons, armor, radio systems, and numerous other components would need to be integrated. It would take years. Meanwhile, the Germans were not standing still. Although the British did not know the full details, Germany was rapidly developing its own jet fighter, the Messerschmitt Me 262. With the massive resources of the Nazi war machine, German development was progressing rapidly. The race was far from over. Whittle was promoted to wing commander in recognition of his achievements. He received honors and public recognition for the first time, but he had little time to bask in the glory. The intense work continued. Improved versions of the engine were urgently needed. Every week counted in the race to get jet fighters operational before the enemy. The period from 1941 to 1943 was one of frantic development. The W2 engine, the more powerful successor to the W1, underwent numerous iterations. Each version improved thrust, reliability, or efficiency. The W2B, developed in 1942, produced 1,600 pounds-force of thrust, nearly double that of the original engine. It was suitable for use in operational fighters. The transition from experimental prototype to mass production presented immense challenges. Components that worked when carefully manufactured by skilled craftsmen now needed to be mass-produced by less skilled workers. Precise tolerances were critical. Variations of millimeters could destroy efficiency or cause catastrophic failures. The supply chain was complicated. Many components required specialized materials and manufacturing processes. Turbines needed to be cast from special alloys and then machined with extreme precision. Combustion chambers required specialized welding. High-speed bearings were extraordinarily difficult to manufacture to the required quality. Whittle also faced growing political and bureaucratic tensions. The British government wanted to nationalize jet engine development, removing it from the control of the privately owned power jets. Established manufacturers like Rolls-Royce and Rover wanted a stake in production, creating conflicts over intellectual property and technical control. In 1942, Rover assumed responsibility for engine production, but the relationship between Rover and Whittle was strained. Whittle felt that Rover made design changes without fully understanding the implications. Rover felt that Whittle was overly protective and didn't understand the realities of mass production. The situation was detrimental to progress. Fortunately, a solution emerged in 1943. Stanley Hooker, a brilliant Rolls-Royce engineer, persuaded his company to take over production of Rover's jet engines. Rolls-Royce had unparalleled expertise in aviation engines and precision manufacturing. The transition was completed quickly, and Rolls-Royce Welland engines, based on the WWII, began mass production. Simultaneously, development of the Gloster Meteor continued. The first prototype flew on March 5, 1943, using experimental engines. Test flights revealed stability and control issues that required significant modifications. But gradually, the Meteor evolved into a capable operational aircraft. In July 1944, almost exactly 3 years after the E-2839's first flight, the first operational Meteors entered service with the RAF. 616. Squadron was equipped with the new jet fighters and began defensive operations against the V-1 flying bombs that terrorized London. It was a historic moment. British jet fighters were finally in combat. However, the Germans had gotten there first. The German Me-262 had first flown in July 1942 and entered operational service in April 1944, 3 months before the Meteor. With a top speed of over 850 kilometers per hour, the Me-262 was significantly faster than any Allied piston engine fighter. It was an unpleasant surprise for the Allies. Fortunately for the Allies, Adolf Hitler had made a crucial strategic error. He insisted that the Me-262 be modified for use as a fast bomber rather than a pure fighter. This delayed its development and limited its effectiveness. Had Me-262s been deployed en masse as fighters from 1943 onwards, they could have significantly changed the course of the air war. The Meteor, although slightly less advanced than the Me-262, was reliable and effective. RAF pilots quickly learned to exploit its advantages. Its superior speed allowed interceptions impossible for conventional fighters. The absence of a propeller improved forward visibility. The flight was smoother and less tiring for the pilots. World War II ended in May 1945 in Europe and August 1945 in the Pacific. Jet fighters had played only a minor role in the conflict, appearing too late to make a decisive impact. But it was absolutely clear that they represented the future of military aviation. The era of the piston engine and propeller was ending. Frank Whittle was promoted to Air Commodore in 1943 and received numerous honors for his contributions. In 1948, he was appointed a Knight Commander of the Order of the British Empire, becoming Sir Frank Whittle. But the honors came with a bittersweet feeling. He received only $10,000 in compensation for his invention, a ridiculously small sum considering the commercial and strategic value of the jet engine. Whittle left the RAF in 1948, physically and emotionally exhausted. Years of intense stress had taken their toll on his health. He suffered from nervous exhaustion and required prolonged rest. He briefly joined BOAC, British Overseas Airways Corporation, as a technical consultant, but soon retired to a quieter life. Meanwhile, the jet engine was transforming commercial aviation. The de Havilland Comet, the world's first commercial jet, entered service in 1952. It could fly higher, faster, and smoother than any previous commercial aircraft. It ushered in the era of mass air transportation, making intercontinental travel affordable and comfortable. The United States, which had lagged behind in jet technology during the war, quickly caught up. American companies licensed British technology and developed their own designs. Within a few years, American manufacturers like General Electric and Pratt & Whitney were producing jet engines that equaled and eventually surpassed British designs. The evolution of jet engines was extraordinarily rapid. By 1950, just 9 years after the E-2839's first flight, jet engines were 10 times more powerful. By 1960, high-bypass turbofans were being developed, offering much greater efficiency. By 1970, supersonic passenger jets like the Concorde were operating. The speed of progress was dizzying. Today, virtually all large military and commercial aircraft use jet engines. The idea that was ridiculed as impossible in 1928 is now the standard technology, enabling billions of people to fly annually. The fundamental principles developed by Whittle remain the basis of all modern jet engines. Frank Whittle lived to see his invention transform the world. In 1976, he emigrated to the United States and accepted a position at the United States Naval Academy. He continued working on advanced engineering projects well into his old age. He died on August 8, 1996, at the age of 89 in Columbia, Maryland. Whittle's story is extraordinary not only for his technical brilliance, but also for his indomitable persistence. He faced rejection after rejection. He was ridiculed as crazy. He worked with minimal resources for years. He watched other countries develop similar technology while he struggled for funding. But he never gave up. Their story teaches us valuable lessons. Truly, revolutionary ideas often face intense skepticism because they challenge fundamental assumptions. Just because something has never been done before doesn't mean it's impossible. Persistence and conviction can eventually overcome all obstacles. When you board a plane today and feel that powerful thrust during takeoff, remember a young 21-year-old cadet in 1928 who imagined a completely new way to fly. Remember the decades of struggle, the sleepless nights, the failed tests and the gradual triumphs. The jet engine changed the world because one engineer refused to accept that his crazy idea was impossible. Frank Whittle didn't just invent the jet engine. He proved that one person with an idea can change the course of history. His legacy lives on in every jet that flies across our skies, connecting continents, uniting people, and making our world smaller and more accessible. This is the story of how one engineer's crazy idea changed aerial combat and aviation forever. End.